Now the same problem, the same example of power absorbed or supplied by an element. So we have now two independent voltage sources. And we are asked to determine the power absorbed. So power absorption by or supplied by each of the element. Okay. So first we calculate I2. So we want to calculate the power absorbed by the 2 ohm resistor in the middle. So hence that is one there. You have to calculate I2 so that then we can calculate the power using this resistor. P equals to half RIM square. Okay. So the P at this 2 ohm equals to half of RIM square, and the resistor is 2 ohm here, and the IM is 6 square. So the I2 here we can calculate using by division by Ohm's law. Voltage here at this node equals to 12 volt here with the phase angle of 30 degree divided by 2 ohm, which equals to 6 ampere with phase angle of 30 degrees. So then the power dissipated by this or absorbed by this 2 ohm resistor equals to 36 watt. Then the power absorbed by the inductor is 0. Yeah, the average power. The average power absorbed by the inductor equals to 0. Now we need to determine the power absorbed or supplied by each of the two voltage sources. In order that we can do that calculation, we need the value current I1 and current I2 as well as current I3. So the current I3 here equals to 12 the voltage source here using voltage using Ohm's law. The voltage difference across this inductor equals to this voltage minus this voltage, this node voltage minus this node voltage. This node voltage is 12 volt with the phase angle of 30 degree, and this one is 6 volt with phase angles of 0 degrees. So the voltage difference across the inductor is 12 volt with phase angle 30 degrees minus 6 volt divided by the current will be this voltage difference divided by the impedance or J1. So from here then we obtain the first we convert this into complex notation. 10.9 plus J6 minus 6 here, 6 divided by J. So this the real part will be this part J6 divided by J equals to 6. Then 10.39 minus 6 is 4.39 divided by J equals to minus J, 4.39. Okay, I hope you all already understand it from the complex mathematical tricks. So from here we reconvert back into phasor format. It becomes 7.43 ampere with a phase angle of minus 36.90 degrees. And the power then absorbed by the 6 volt, since now the current is enters from the positive pole, we know from passive sign convention, it means that this voltage source absorb power, not supply power. So it means then the power absorbed by the 6 volt voltage source equals to half times the voltage times the current cosine the phase difference between the voltage and the current. So half times 6 times the maximum current, 7.43 cosine 0 minus 36.90 degree or plus 63 cosine 36.19 degrees. The value equals to 18 watts. Yeah, remember this is using passive sign convention, means when the current enters from to the positive terminal, it means that that element absorb power. So the absorbed power will be equal to positive. Then we calculate I1. I1 equals to I2 plus I3. So I2 is here, okay, 6. It's first angle 30 degrees, or when converted to complex notation, equals to 5.20 plus J3, and I3 equals to this, or equals similar to this one, plus 6 minus J.39, J4.39. So then the I1 will be equal to 11.2 minus J 1.39 ampere, and reconvert back into phasor format, it becomes 11.28 with angle minus 7.07 degrees. So the power at this voltage source may be equals to half times the voltage maximum, which is 12, times the current maximum is 11.28, cosine the phase angle difference between the voltage and the current. Yeah, 30 minus 7.07, or 30 plus 7.07, and the result is minus 54 watt. Yeah, everyone understand, yeah, why this is minus? Because according to passive sign convention, since current is leaving the positive terminal, it means that the power absorbed by this voltage source equals to minus 54 watt. Or in other words, that this voltage source supply power. Okay. And if you look here, then this minus 44 watt basically equals to 18 plus 36 watt. So the value is correct based on the Telegrand's theorem. Okay, another example here, determine the power, average power absorbed and supplied by each of the element. We have two independent source. One is a voltage source, another one is the current source. We have two passive element, resistor and capacitor. Let's try to solve first using the current, finding the current using loop analysis, or Kirchhoff voltage law. Here we apply two loops, I1 and I2. I1 is clockwise, I2 is counterclockwise. And so we can then derive the two loop equation. At the loop 1, then the I1 will be equal to the 12 ampere with the phase angle of 0. At loop 2, voltage here for volt with phase angle 30 degree equals to, according to the loop direction, minus J2 times I2 plus 4 times I2 plus I1. I2 plus I1 equals to here 12 phase angle of 0 degrees. So from here, then we can calculate I2, the current at this branch here, this loop, for phase angle 30, phase 30 degrees, minus here for times 12, equals to 48, minus 48, 0 degrees, divided by 4 plus J2, okay, to find the I2. So from here, we convert first into complex format to obtain here, and we convert back to phasor format. So we obtain 44.58 with an angle of 177.43 degrees divided by this denominator. So this will result in a current I2 equals to 9.97 ampere with phase angle 204 degree. So the voltage at the 4 ohm will be equals to the 4 ohm resistor multiplied by the I1 plus I2. This current 12 plus 9.97 phase angle 204 degrees. Okay, so from here we obtain 19.92 volts, phase angle minus 54.5 degrees. Alternatively, actually, we could also use node equation. The first node at this node, because current is entering, so minus 12 ampere, plus V 4 ohm minus 0 divided by 4 ohm, plus V for at this node minus 4, with phase angle 30 degrees divided by minus J2. This is the first node equation. Second node equation at this node, then goes to 4 minus V 4 ohm divided by minus J2 equals to I2. The power then at 4 ohm will be equals, we can use this formula. Okay, so since voltage is already known here, so P at 4 ohm equals to half times the Vm squared divided by R. The R is, where is it? 4 ohm. Yeah? So now Vm is this one, 19.92 squared divided by 4. We obtain the power being absorbed by the 4 ohm resistor equals to 49.6 volt. The power at the capacitor the average power absorbed by the capacitor will be 0. Yeah? So it does not dissipate power. Then let's see the power being absorbed by the 12 ampere current source. So since the supplying current, so here according to the passive sign convention, it equals to minus half times the voltage here is 19.92, okay, times the current is 12, cosine the phase angle difference, minus 54.5 minus 0. So then we obtain minus 69.4 watt power being absorbed. It means actually the current source is supplying power. The power at this voltage source will be equals to power absorbed by passive sign convention, since current is leaving this voltage source, so we assign this negative value as well. It means that this is supplying power. And we obtain negative half times 4, the voltage, times the current I2 is 9.97, I2 max is 9.97. The cosine of the phase angle difference is 30 degrees minus 204 degrees. Okay, 30 degrees minus 204 degrees. 30 degrees is this angle, and 204 is the angle of the voltage, of the current here. Okay, and the value here, the difference will be how much? Cosine negative 174. 174, or the same as cosine 174 degrees, which means the value of this is negative, because the cosine of an angle above 90 degrees and until 270 degrees negative. That's why then it becomes positive. It means this voltage source is absorbing power. So if we check again, according to Tangerang's theorem, voltage power supplied should be equal to the power absorbed. The power supplied is by this 12 volt current, 12 ampere current source, minus 69.4 should be equals to power absorbed 19.8 plus 49.6. Yeah, and this is correct. 49.6 plus 19.8 equals to 69.4 watt, which is equals to the power being supplied by the 12 ampere current source. Okay, clear? Any questions? So you use Tangerang's theorem, or you can use the Tangerang's power supply to power absorb to get the value, but then you can check using the Ohm's law to determine the current first, the power, and then current and the voltage, and then calculating the average power. Then the two values should check to each other in different way. You first calculate the power, the voltage and the current, and then you calculate the average power absorbed. Then you check using this Tangerang's theorem. Power supplied should be equals to power absorbed. Okay, depending on the questions. Okay, another more complex circuit. Determine the average power absorbed or supplied by each of the element. So we have two independent sources, 12 for the 24 volt voltage source and 12 volt voltage source. We have two resistors and one inductor. Using a node analysis, KCL, Kirchhoff current law. Using this node, the first node here, V minus 24 divided by 2 plus V minus 12 divided by J2 plus V minus 0 divided by 4 equals to 0. Okay, simplifying from that equation, so we obtain here multiplied by 2J, multiplied by 4J. Here, so we obtain here 2J times V minus 24. Here we obtain 2 plus 2 times V minus 12 plus J V equals to 0. So from here we simplify further and we obtain the voltage equals to 14 voltage at this node equals to 14.88 volt with a phase angle of 7.125 degrees, or in complex format 14.77 plus J 1.85 volt. Okay, then the current I1, you can calculate current I1 from this voltage here, 24 minus this V divided by the 2 ohm. 24 minus this voltage, not voltage here, 14.77 minus J 1.85 divided by the 2 ohm. Then we obtain I1 to be 4.62 minus J 0.925 ampere. Yeah. Or in phasor format, I1 equals to 4.71 with a phase angle of minus 11.32 ampere. What about I2? So I2 can be calculated using this. If I2 is directed upward, yeah, so using this voltage minus this node voltage divided by J2, like this. So we obtain I2 to be equals to minus 0.925 plus J 1.385 ampere, or in phasor format 1.67 phase angle 123.73 ampere. So then I3 here, so P at the 2 ohm resistor here will be equals to half times the voltage, or we use this formula instead. Yeah, no need to use voltage. Half times the resistor value times the current, I1 square. Yeah, I1 square here equals to 4.71 square. So the value of the power absorbed by the 2 ohm resistor is 22.18 watt. Then the power absorbed by the 4 ohm resistor is half times voltage here. So we don't need to calculate I3 because we already know the node voltage here, and the voltage here is 14.88. The value maximum is 14.88 squared divided by 4 ohm. We obtain 27.67 watt. The power absorbed by the 12 volt voltage source here using passive sign convention, since current is leaving it, so the power absorbed is negative. It means that we assume that it is supplying power. So minus half times 12 times here 1.67 cosine the phase angle difference 0 minus 123.73. Since this is above 90 degree, and we know that the value will be negative, yeah, for cosine. So the negative times negative is positive. Positive 5.565 watt. So we know that this voltage source is absorbing power. The power absorbed by the 24 volt voltage source is minus half times 24 times 4.71 cosine 0 degrees. Yeah, this 0 degrees plus the phase angle of I1 is negative 11.32, so or plus 11.32 degrees. Okay, so then the power absorbed by the 24 volt voltage source here equals to negative 55.42 volt. It means that this 24 voltage source is supplying power. Okay, then we can check using Telegrand's theorem. Yeah, the power absorbed is the one that positive value, 22.18 plus 27.67 watt plus 5.565 watt. The power supply is 55.42 watt. Are they equal? Yes, they are equal. Yeah, this is more or less around this value. Okay, any questions? Quite clear, yeah, I think. Okay, now we learn a new concept, the maximum average power transfer. What is the maximum of power that can be transferred by an AC circuit into a load? So the AC circuit is represented by the Thevenin equivalent voltage source, or the VOC here, in series with a Thevenin equivalent impedance ZTH, and they are connected to the load impedance ZL. Okay, so the voltage seen by the ZL is VL here, and the current flowing through the impedance load, the load impedance is IL. The Thevenin impedance ZTH is basically contains RTH, resistive component, as well as the reactance components J plus XTH. Similarly, the impedance loading, the load impedance is also consists of RL, the resistive part, and J plus JXL, the reactance part. Then the average power at the load, it will be equals to half the voltage of VL here, voltage across the load, the maximum amplitude, VLM, times the maximum amplitude of the current flowing through the impedance, through the load, the ILM, cosine the phase angle difference between the voltage and the current of the loading, the theta VL minus theta IL. Or, so basically then VLM is the magnitude of VL here, and the magnitude of VL, and times the magnitude of IL. And VL basically from voltage divider formula can be calculated from the V open circuit as equal to ZL divided by ZL plus ZTH times the V open circuit. Then the current IL flowing through the load equals to the VL divided by ZL. So it means then the VL, basically the magnitude of the VL equals the magnitude of ZL divided by ZL plus ZTH times the magnitude of the VOC. And from here, from the current flowing through through the load impedance, the phase angle of the load current equals to the phase angle of the load voltage minus the phase angles of the load impedance. Okay, so the phase angle of the load impedance basically is the phase difference based on this between theta VL and theta IL. The load difference, the phase angle difference between the load voltage and the load current. The magnitude of the load current will be equal to the magnitude of the voltage, load voltage divided by magnitude of the load impedance. Okay, the load impedance equals to RL plus JXL. And the phase angle of the cosine of the phase angle equal to 1 over square root of 1 plus tangen square theta. And the tangen of the phase angle of the load impedance equals to the ratio between the reactance of that load divided to the load resistance. Okay. And this is basically equals to this VL cosine of VL, the difference between the load voltage and load current. And then equals to RL, its cosine equals to RL divided by the square root of RL square plus XL square. Then the power, the average power at the loading equals to, calculated from this formula. Okay. VL is obtained from here. So this equals to ZL divided by ZLTH times VOC multiplied by RL. The value of RL is equals to this one, PL divided by ZL. So VL we insert again this one. Okay, so that is why the ZL plus ZTH denominator is squared, and VOC also squared. The ZL is supposed to be squared, but divided by the ZL here because only ZL. Multiplied by to the cosine, and here cosine of the phase angle difference between the voltage and the current at the load, or equals to this, RL divided by square root of RL square plus XL square. Okay, since square root of RL square plus XL square basically is the same as the magnitude of ZL. Okay, so from here, okay, then this cancel each other. From there, we obtain then ZL plus ZTH will be equals to the real part of each of them, the RL plus RTH, plus the imaginary part is J of the reactances of the load and the reactance of the Thevenin equivalent impedance. JXL plus XTH. ZL plus ZTH square will be equals to this square plus this square. Okay. So from here, then we obtain PL equals to half of VOC square divided by this one equals to RL plus RTH square, okay, plus XL plus XTH square. Okay, so this is equivalent to this upper part, but now we replace ZL and ZTH in terms of the resistances and the reactances. Then from here that the change of the power to the transfer to the load as a function of XL will be 0. Yeah, the change the dou PL to RL to the load is also 0, which means then the XL should be equals to minus XTH. So this occurs when the power is at maximum. Yeah, so that then the gradient is at 0 from calculus. You know, when the value of a function is maximum, it means that the gradient is 0. So dou PL as a function of dou XL should be equals to 0. Dou PL towards dou RL should be equals to 0. Dou here represents partial derivative. So when the gradient is 0, it means that the XL should be equals to minus XTH. When XL equals minus XTH, then this equals minus 2 XTH. And RL should be equals to RTH. Okay. So when this is XL equals to minus XTH, so this value equals to 0. There is no reactance component. What occurs? And the RL equals to RTH means this will be 2RTH squared. So the optimum, the maximum average power transfer at the load is obtained when the value of the impedance of the loading equals the conjugate value of the Thevenin impedance, Thevenin equivalent impedance. Yeah, because the RL equals to the RTH, the real part is the same, but the imaginary part is conjugate to each other. XL equals to minus XTH. Okay. So the PL max, calculating from here, so this will be 0, right? And this will be equals to 2 RTH, or being squared, so 4 RTH squared. But for RTH, then this equals to RTH, to cancel. So for RTH, the denominator will be only becomes to 4 RTH, and this equals to 4 VOC being squared. So the power is being transferred at maximum to the load when the impedance of the loading equals the conjugate value of the Thevenin impedance of the circuit, as the AC circuit, and the maximum power being transferred equals to half of the VOC squared divided by 4 RTH. Okay, let's learn from some problem here. Find the ZL, the impedance of the loading, for maximum average power transfer from the left part to this loading. Compute the maximum average power supplied to the load. Okay, from the previous, the formula derived in the previous slide, the optimum load impedance should be equal to the conjugate of the Thevenin equivalent impedance of the left part of the open circuit. And then the PL, the power maximum power, will equal to half of the V open circuit square divided by 4 of the resistance, equivalent Thevenin resistance. So first we have to find the equivalent Thevenin voltage source VTH and the equivalent Thevenin impedance. Remove the load here first, and determine the Thevenin equivalent of the remaining circuit. For the ZTH, so the current source becomes open circuit, right? So the ZTH is seen from this terminal. This basically, this one is in series. Okay. For the ZTH here equals to 4 ohm in parallel, and this in parallel with 2 plus J1, plus 2 plus J1. Yeah. So for calculation, we obtain this value in complex format or in phasor format. You can also calculate this value equals to 1.47 with a phase angle 16.93 degrees ohm. So this is the Thevenin equivalent impedance. Then the optimum load impedance will be conjugate of this Thevenin equivalent impedance, which it equals to 1.47. The conjugate is at the other quadrant, negative, with having a negative phase angle of this minus 16.93 or 1.41 minus J 0.43 ohm. Okay, so this is, so we already answered the first question, the ZL for maximum average power transfer based on this formula derived in the earlier slide. Then second question is to compute the maximum power. In order to compute the maximum power, using this formula, the RTH is already found here, 1.41, but then we need to calculate the VOC, the Thevenin equivalent voltage source. Okay, then the VOC here basically can be calculated by 4 times the I1, the current here, and I1 can be calculated using current divider formula, which is 2 divided by 2 plus 4 plus J1, 6 plus J1 times 4 ampere. Okay, so here we obtain the V open circuit to be 5.26 volt with a phase angle of minus 9.64 degrees. So the PL max then equals to half times COC, 5.26, the magnitude of the open circuit voltage, 5.26 square, divided by 4 times RTH. 4 times the RTH, the Thevenin equivalent resistance, is the real part of the Thevenin equivalent impedance, which is 1.41 here. So then the maximum power being transferred, maximum power transfer occurring at the optimum impedance is equals to 2.45 watt. Okay. Give another example here. Now with dependent voltage source now. Find the ZL for maximum average power transfer at this load. Okay. Then afterwards compute the maximum average power supplied to the load. Okay. Then again, this is the basic formula derived already earlier. the optimum power transfer occurs when the loading equals to the conjugate of the Thevenin equivalent impedance of the this terminal. Then the PL max equals to half times the VOC square divided the open circuit voltage square divided by 4 times the Thevenin equivalent resistance. Now, since this is a circuit with dependent sources, so we have to calculate. You cannot just short circuit or open circuit. Yeah? We have to find the open circuit voltage and the short circuit voltage, and calculate the the Thevenin equivalent impedance as VOC divided by ISC. So VOC is like this. So VOC here, since it is not connected, basically the same as this voltage. Okay. Then using KVL, like this. So this is -4 plus -4 negative Vx dash plus 2 plus J4. Okay. Well, Vx here equals to the negative of since 2 times, since the Vx is positive here in this part, while the current is flowing from into the negative terminal, so the Vx this equals to negative 2 times I1. Yeah, this is I1. From there, from these two formulas, then we substitute minus Vx here. Yeah. So equals to 4, this is -2, minus and minus equals to plus 2I1, yeah, plus 2I1 equals to 4I1 plus J4I1. Yeah. So it means the I1 equals to 4 volt here divided by 4 plus J4, or 4 square root 2 with the phase angle of 45 degree. Hence, we obtain the results 0.707 with the phase angle of minus 45 degrees ampere as the value of I1. Okay, KVL at the second loop here, so VOC will be equals to 2I1 here, 2 ohm at this 2 ohm, -4 degrees here. At this capacitor, there is no current flowing, yeah, because it is floating open circuit. No current flowing through this capacitive component. So from here, we obtain VOC equals to -3 minus J1, or square root of 10 with a phase angle minus 161.5 degrees. So we obtain already VOC. Now we need to find the short circuit current. This is the short circuit at the load. Okay, we have to find this ISC. We use loop analysis using Kirchhoff voltage law for the short circuit current. So at this part is minus V double dash X, okay, plus J times 4I plus 2 times I minus IC, then minus 4 volt with the phase angle of 0 degree equals to 0. Then at this loop, 4 plus ISC minus I times 2 ohm minus J 2 ohm times ISC equals to 0. Okay, and the control variable here V double dash X equals to negative or equals to 2 times ISC minus I. Substituting and rearranging from the first and second equation, substituting V double dash X here with this value. So we obtain 4 plus J4I minus 4 ISC equals to 4. And from here, we obtain minus 2I plus 2 minus J2 ISC equals to negative 4. Okay. Then from here, we obtain the current equals to 1 minus J1 plus IC plus 2, and 4 times like this, Then the current ISC from here we obtain as equals to -1 minus J2 ampere, or in phasor format as square root of 5 with a phase angle of minus 116.57 degrees. Then the open circuit voltage is from the previous slide. Yeah, so okay, yeah, this value minus 2I1 minus 4 volt. Yeah. So from here, then we obtain the ZTH VOC equals to VOC divided by ISC. Okay, so using this phasor format, so we obtain square root of 2 minus 45 degree phasor equals to 1 minus J1 ohm. Then the Z optimum will be equals to 1 plus J1 ohm. Okay, the conjugate of the Thevenin equivalent impedance. So from here, then we can calculate the maximum power, half times VOC. Yeah, the magnitude is square root 10, yeah, being squared, divided by 4 times RTH. The RTH is 1 ohm, yeah, 4 times 1. So we obtain the maximum power being transferred when ZTH, when the ZL equals to the conjugate of ZTH is 1.25 watt. Okay, let's have another break.